Quantum computers. The computers we use today are made up of a large number of transistors. Early computers contained a very small number of transistors, but today it has grown to billions. As the number of transistors increases, so does the processing power of the computer. In this way, as the processing power continues to increase, the transistor has to be reduced in size. This means that the number of transistors per unit density is increasing. According to Moore's law, the number of transistors in an integrated circuit doubles every 2 years. When the size of a transistor is getting small, then the quantum properties described in quantum physics can be seen in electrons. For an example, when a transistor is used as a switch, it allows electron current to flow through the transistor during saturation. During the cutoff, it stops the flow of electrons by creating a barrier to the flow of electron current. Even though it creates a barrier to current flow during the cutoff, when the transistor is getting smaller, the electrons are likely to emerge from the other side of the barrier due to the quantum properties of the electrons. This phenomenon is called quantum tunneling. Even though technology has advanced to make a transistor even smaller, this quantum feature makes it useless. So, since the size of a transistor can no longer be reduced in this way, the best thing to do is to create computers using quantum properties of very small particles such as electrons. This is where quantum computing comes into play. A classical computer works in bits. The possible value for a bit are 1 and 0. On a classical computer, the value 1 is usually denoted by plus 5 volts, 0 represents 0 volts. We can get 2 combinations in 1 bit. Likewise, we can get 4 combinations in 2 bits and 8 combinations in 3 bits. In this way, if there is an n quantity of bits, a quantity of 2 into the power of n combinations can be obtained. But here, only 1 combination exists at a time. The bits in this typical computer are called classical bits. The bits in this quantum computer are called qubits or quantum bits. A qubit also represents the value of 1 and 0, but in different way than a classical computer. Here, a quantum particle is used as a qubit. Usually, an electron is used here. A quantum bit also represents the 2 values 1 and 0. According to the spin direction of the electron, spin up is considered as 1 and spin down is considered as 0. The spin direction can also be considered as spin right and spin left. This is generally considered as spin up and spin down. The spin of this quantum particle cannot be compared to the spin of a ball in ordinary naked eye. Classical physics breaks down when it goes to the subatomic particle level. Quantum physics is valid here. So, an electron has an angular momentum. If we measure it in a certain direction, we can measure an angular momentum in one of these directions, either to the direction in which we measure the angular momentum or in the opposite direction. No matter which direction we measure in this angular moment, it does not drop to 0 in any direction. We always get measurements of angular momentum in the direction we are measuring or vice versa. Depending on the direction of this angular momentum, the spin direction is considered as spin up or spin down. The spin of an electron is a complex behavior. If you are interested in this, study in depth. You will definitely be amazed. Quantum computing uses 2 main features of quantum particles. They are quantum superposition and quantum entanglement. During superposition, the electron can coexist at different states. The existence and behavior of electrons during superposition cannot be determined. During superposition, the electron can hold the both spin up and spin down states. If we measure this, the electron collapses in one of 2 states, spin up or spin down. Take a coin toss for an example. When a coin is flipped over and rotated in the air, it is impossible to say for sure whether the coin exists head or tail. It is also impossible to say for sure what the value will be after the coin falls. If we catch the tossed coin in our hand and look at open palmed, we get one of 2 values, either head or tail. This example gives an overview of what is quantum superposition and measurement. Schrodinger's cat is a well-known example that explains superposition. Quantum entanglement. If a quantum entanglement occurs between 2 particles, the 2 particles will no longer behave independently. The quantum state of one particle depends on the quantum state of the other particle. If we know the quantum state in which one particle exists, we can tell exactly what state the other particle exists in. So this feature is also used in quantum computing. If 2 electrons are entangled and if one electron is in spin up state, the other electron will obviously be spin down. Another feature of this entanglement is, even though these 2 entangled particles move to the farthest point in the universe, the bond between two electrons remains the same. Suppose one electron is left on the Earth and the other is carried to Jupiter, but the bond between two does not change. Okay, let's consider quantum bits again. So you can create different combinations from these qubits as well as classical bits. For example, you can get 8 combinations from 3 qubits. If there is an n number of qubits, you can get 2 into the power of n combinations. The difference between classical bits and qubits is that classical bits can only exist in one combination at a time, but the feature called superposition allows qubits to exist in all combinations at once. So due to this feature, a quantum computer can do different calculations much faster than a classical computer. But a classical computer cannot be completely replaced by a quantum computer. In 1996, David DiVincenzo introduced the 5 minimum requirements to create a quantum computer. This is called DiVincenzo's criteria. Number 1. A scalable physical system with well-characterized qubits. Number 2, the ability to initialize the state of the qubits to a simple fiducial state. Number 3, a universal set of quantum gates for long relevant decoherence times, much longer than the gate operation time. Number 5, a qubit specific measurement capability. So these are some basic facts about quantum computer. Advances in quantum computers increases the processing power of a computer and also pose a major threat to data encryption method used for data security. Quantum properties can be used for some cryptography tasks too. For example, quantum properties can be used to stop a third party from reading information that we communicate to someone via digital signal. So we will talk more about these things in the next video. Please leave your comment below.